Um, so welcome to 140, lecture 18. Coronavirus has spread us far and wide. Um, um, a few check-ins before we get going. First, I hope all of you guys are staying healthy and staying away as much as possible from anybody and staying isolated. I know it's really hard and it's really strange to have classes set up online. Um, I can tell you, though, the skills that you're picking up now of video conferencing are going to be really important when you get into the professional life, because we do this every day. um, and if you think having a lecture online is weird, tomorrow, 8 of us from my office will be interviewing for a project on Zoom. So everyone from our office and all of the clients will be all at their homes also interviewing in a really weird setup. So I'll report back next week how that goes. So yeah, it could be super strange. A couple things for today. We're going to still be doing the poll everywhere polls that you guys did with Gail on Monday. So have your phones close by. As well as this week we're going to be doing, or today we have a quiz. That quiz is going to be set up in B course. Take your time, but it'd be a good idea right now to open up B course in a separate tab and just have it behind. When we actually get to the quiz, we'll give you instructions, and there's plenty of time for it. So no need to panic, but it'd be a good idea if you could log in now. And then overall, I just want to hope everybody is hanging in there, and all your other courses have transitioned okay over to Zoom or whatever digital format you guys are following. For today's lecture, I hope all of you can open up the group chat window. So if you go down to your control bar, there's a little section to open up the chat. I'll have it open, and our GSIs will also have it open to be able to follow along. So if you have questions, feel free to type them in there and we'll try to respond live. If there's something I don't get to during the lecture, I'm happy to follow up afterwards and send out a note on eCourse. So with that, let's see, sorry, first question, will the quiz be under? We'll give you guys instructions when we get to the quiz. We'll give you a link to follow online, so don't worry about that. And like I said, we'll have plenty of time, but we'll show you where the quiz is on bCourse. Okay, so with that, we're gonna jump in today. So today's topic is embodied carbon and looking at a little bit more holistic full life cycle carbon and climate impact from projects. Since I can't walk around, which is what I normally do when I lecture, you'll probably see me moving around. So I apologize if I am hypnotic and or make you seasick, but we'll keep going. So one of the first things that when we talk about life cycle carbon impacts or embodied carbon impacts, a big piece of that is the language that we use to talk with our clients. So I'm out with clients every week talking about the importance of both the energy topics that we talk about in 140 and also trying to come up with a convincing language to get folks on board for energy efficiency and resiliency and some of the other topics that we talk about in 140. The good news is over the last sort of 5 years, that job has been much easier. This is just some Gallup poll data coming in, just showing that society-wide, people are starting to, across the US, are starting to pick up the idea that climate change is actually really important, and we need to, and you can't have economic growth that's sustainable and equitable if we don't talk about climate justice and environmental justice. So that's really exciting. The other piece that's changed in the last 5 years or so that's made it a lot easier is that with certain lack of leadership at the federal level, there's been a big push locally and a lot of grassroots efforts that have brought up idea of carbon as a really important metric. And people generally saying that there's a good reason to believe the science out there. So even though you might hear otherwise in the news, the people are with us, and this is a really good fight. So in a second, we're gonna do our first poll everywhere quiz, or poll everywhere poll, but it's coming up. Don't worry, we're gonna give you the link, and there'll be plenty of time. It's meant more to get feedback from you guys than to cause any panic. You've seen me present this graph before, or something very similar to it. And the reason that I do is because today we're going to be talking about the importance of focusing on climate in the next 15, 20 years, and why looking out past that when we talk about energy efficiency might not be the only message that we want to convey. So there's a really strong importance to focusing on all the forms of carbon emissions in these next years. And that's where this idea about embodied carbon comes into play, because it's not just about emissions going forward. So before we get there, this is going to be our first poll everywhere question. So get your phones out. You're going to text Gail Brager 190 to the phone number 37607. That'll let you join into the poll. And then you're going to, hopefully once you've done that, you'll get a little message from them saying you're in, which is great. So the question is, have you heard of embodied carbon? I'd like to get just a sense of where the class is at for that.
Okay. So, and then Stet, if you can, when I went to full screen, I lost the Zoom controls. So if you can share, if you're able to change, or one of the GSIs can change and share my screen, I'm able to then show the results real time.
Okay, I stopped sharing, so hopefully that will let you.
Yeah, but I can't do it. I think because when I went to present, it was in presenter mode. So now both of my screens are full image. I can't find my Zoom control. So one of the GSIs or you can just share my screen. We're trying this, students, for the first time of swapping back and forth.
Swapping back, we'll see.
Yeah, because Stet doesn't have the poll everywhere software.
Let's see if I can get you. Oh, wrong question. I don't have control of your screen.
All right, let's see if I can just. Okay, we're gonna try it. Maybe it's a different order. Share screen. And then we're going to present. Okay, can people see my screen now?
No.
Not yet.
Okay, nope. One of GSI's who are co-hosts, can you go to my name and the participants and share screen? See if you're able to do it. And thanks, students, for being patient. We're trying these technologies in real time here.
Trust us, we're professionals.
I don't think you can force share somebody else's screen.
You don't think what?
I don't believe you can force share somebody's screen.
Oh, okay.
Yeah.
So let's see. Let me see if I can try this again. Share screen.
Oh, something's happening. Here we go.
Okay, so now we're gonna get this to work because I'm so excited about being able to go back and forth. Now can you see
yes.
it?
Yes, we can.
Okay, so what did we learn from that? I have to share the screen and then go to PowerPoint mode.
Yep.
Got it. Thank you.
Awesome. But this is really exciting. So so everyone, this is phenomenal. So 3/4 of you almost have already heard of embodied carbon. For the 28 or so floating around, third of the class that hasn't, don't worry, we'll catch you up. But this is really exciting that it's within your sort of vernacular right now in terms of everyday conversation. So that's really, really exciting.
Okay, so now I need to stop sharing.
Stop sharing, and and I'll hop.
Okay, I stopped sharing. I think you can share.
Yep, I'm coming back in.
We're gonna do this a couple times today, so the next time I think we're gonna be just really smooth.
Okay, perfect. I'll give it a chance for the lag in case anyone has any slow internet connections, but you should hopefully be able to see my my screen in a second if it's not already up. Okay, so when there's a lot of ways that we can talk about carbon, and embodied carbon is one of those ways. But I want to give you guys what the global perspective is when we talk about full life cycle carbon assessment and what those languages mean. So typically in this class, we've focused mostly on what we would consider scope 1 emissions, like how much energy does our building use on site. And so all of the things that we've done so far in this class, so the whole building heat loss transfer, solar control, shading, the daylighting stuff that you guys have been working on, even Gail's lecture on Monday on passive cooling, all of those strategies have really been focused on trying to limit our scope 1 emissions. And scope 1 emissions of the 3 scopes for a full life cycle carbon assessment are all those emissions associated with operations in the building. So once the building starts, for all those years that it runs, how many greenhouse gas emissions or carbon equivalents are emitted through that operation. When we talk about full life cycle carbon, though, we're actually going to be looking at all of these other streams of what we call scope 3 emissions, are all the pieces that are required to make that building happen. And so those tend to be outside. If we drew a dashed line around our building, things that are happening outside our building, but facilitate the construction of our building would fall under scope 3 emissions. So these are outside our boundary, but they're really important. So if you think about all the materials used that go into a building, the concrete, the wood, nails, glass, glazing systems, roof constructions, all those materials, they need a certain amount of energy to be extracted if they're mining based. There's usually some manufacturing energy associated with those. So the energy that a manufacturing plant uses to make the thing that we need to build the building, there's emissions associated with that. And then getting that material to our site has emissions associated with what kind of transit, whether it came on a ship, whether it came on rail or traditional overland truck shipping. So each of those avenues have different carbon intensities. So you have, for instance, travel by ship, because of the sheer quantity of materials that they can fit on a ship, has relatively low carbon emissions relative to single truck shipping. So a single truck bringing something a really far distance isn't a carbon smart way to ship something. And rail is amazing because of the low friction on a rail system. There's far less carbon emissions associated with that. So when we think about building materials, not only do they have a weight associated with them, but they have this whole history, this carbon history associated with them that goes into what we would consider embodied carbon, the amount of carbon that was associated with the construction or procurement of that material. So when we talk about, a lot of, in this class, we've focused on operational carbon. And if you look across the entire world, we have a lot of square feet or square meters of building materials, and they emit a ton of carbon in operations. And that's been our focus for years. We've been like efficiency, 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 140, tooting the horn. It's really exciting. We want to focus on that. However, that's not the whole story when we think about the carbon emissions associated with climate change. And so you've heard us talk about building new net zero energy buildings, more efficient buildings. If we just built new, it'd be better. One of the problems with that is that we typically are building new construction in areas that are already built up. And so if we think about this blue line, sort of an overlay of embodied carbon, every time we tear down a building and we build a new building, we're actually taking embodied carbon that we already spent years ago, maybe 50 years ago. That carbon has already been released in the atmosphere. We're taking that and we're putting it in a landfill, and it has a certain carbon associated with that. And then building a new building in its place has a whole new layer of embodied carbon. This idea that we should tear down buildings and build new, more efficient buildings, yes, they'll have lower emissions in operations, but we're still emitting all of that embodied carbon. And that's And that is really kind of an important thing to keep in mind. So yes, building net zero energy buildings is fantastic, and I get super excited about it. That's most of what my career is. But remember that building new buildings, even if it's a net zero energy building, emits carbon. The embodied carbon can still be a really large piece. So something that we're going to talk about today, and I'm going to talk through a couple case studies later this morning, of rather than tearing down buildings, what if we focused on retrofitting poorly performing buildings to net zero energy or net positive energy? If we looked at the area under this curve, the idea is instead of tearing down existing buildings completely, what if we renovate them? We leave the embodied carbon that was there for most of the stuff, and we just change out the building materials that we need to make that a modern building. So try to leave the structure in place, add insulation, add efficient systems, add maybe better glazing, better windows to make that building much more efficient, so we can still make it net zero, but we don't spend a whole new building's worth of embodied carbon. So that's kind of our goal, and professionally, that's definitely one of my goals in projects, is to, rather than start every building or every project with the thought of a new building, look for opportunities to reuse existing buildings. So when we look at building materials and embodied carbon, there's a lot of folks are like, okay, what if we just take our typical building and we just swap out maybe 5 materials for things that have lower embodied carbon? And that's a great strategy, super amazing. Often that one-for-one swap isn't going to provide you with a tremendous amount of embodied carbon savings. So in this example, let's say we're just building a typical house, maybe in the Midwest, so it has a full basement. Was there a question? Sorry. Nope. Okay. So say we're building a typical building in the Midwest. It's got a full basement, which means site work, so excavation, concrete walls, etc. That's going to have a certain embodied carbon. And if we just thought about swapping out with greener materials, so maybe instead of fiberglass insulation, we went with cellulose insulation. Instead of vinyl windows, we went with wood windows. Maybe instead of OSB as our shear system or our backer board, we're going to look at plywood. It actually has a slightly lower embodied carbon. And if all that concrete, even in a good design, we are hoping to do fly ash substitution. In our improved one, we had even more fly ash. So we could get about a 7.5 ton reduction. But most of the embodied carbon that you're going to look at in buildings is just associated with the sheer size and volume and weight of what you're building. So this is where bigger is not better. When we talk about embodied carbon, designing smart, smaller, more compact buildings if possible, if your program fits in it, is a much stronger strategy. So the example on the far right is, okay, let's do all those green material swaps, but in this case, could we get by with just not building the basement? Which obviously there's a program conversation there about, well, now I don't have space, and do I need to build bigger, etc. But just to give you an idea of what that site work reduction and what that reduction in concrete would offer, almost 4 times the amount of carbon savings than doing the green material swaps. So size really matters when it comes to embodied carbon and the strategies and materials that we use. Okay, so for the second poll, I'm going to walk you guys through a case study in a little bit, but first I want to talk about insulation and insulation materials. So for the first poll, again, we're going to do the same process, but the question this time is, which type of insulation do you think has the highest embodied carbon? So if you were to pick an insulation material, which one do you think is going to have the highest embodied carbon of the available options? So hopefully, Gail, you can.
I'm working on that right now.
Share your screen again.
Let's see what happens. Okay, can people see the screen?
Yes. Yes.
Yay! That was smoother.
Okay, who are the 3% that said on insulation? We can track you. No, okay.
We can't actually,
Yeah.
but I'd like to. I also
Yeah.
want to note that on this screen, which we didn't put on stats, but I should in the future when we're doing this kind of swap, you could see at the top of this screen, there's also an online option. So the whole idea with texting is that we tried this at the last lecture. You have to text Gail Brager 190 to that text number first, and then you answer the poll. And if that still doesn't work, you can go online. But we don't want anybody to panic. We are not using poll everywhere for quizzes. We are not using it for attendance. We don't know who's answering what. We're just trying to be a little bit more interactive. So no stress if this doesn't happen.
Yeah.
All right. So now
Awesome.
I'm going to, so now I have to find, let's see, are we back? Stop share. Okay, now we got it. Now you can share again.
Okay, I am coming back. Hold on. Here we go.
Are you able to control your own sharing? Yay! Look at us, Stat.
I know, we're amazing. Sometimes I amaze myself that we can get through this at all, but
I think between the two of us, we've got half a brain this morning.
Yeah. Okay, so also, the responses are great and they're totally true. So you guys are rock stars in terms of actually the way that you guys responded, where XPS had the highest. Most folks thought XPS foam had the highest embodied carbon. Totally true. The next one of that group that I gave you is fiberglass, and the least amount is cellulose. And we talked about cellulose; it's essentially recycled newspaper. But it's not the whole story. And I wanted to share with you guys a link at the bottom. So down here in the lower left-hand corner, you guys can see a link. This is for an Excel spreadsheet that was developed at Building Green, which is a great resource. If you guys aren't familiar with Building Green and you're interested in sustainability, I highly encourage you to follow their blog and their website. They have amazing articles, and they tend to be written by experts in the field. So highly encourage you, if you're interested in this sort of stuff, beyond 140 to dive in. But there's an Excel spreadsheet there that will let you compare the total global warming impact from your decision on an installation. And so you can select in there, you're going to select your region. So you'll notice there's an input on the spreadsheet for heating degree days. And that is a fantastic means to, that's going to give you your climate specific information. And we use those same heating degree days when we were doing the whole building heat loss. So you already have those numbers, you totally know where to find them. And you plug them in, you can put in the R value, or what source of energy you have, the efficiency, et cetera, and how long you think your building's going to last. So 50 years, 25 years, 100 years. And it will plot out for every R value. So if your wall is a R value of 10 to 40 to 60, it's going to look at the combined global warming potential of both the embodied carbon and the energy that you would save by adding more insulation. And the really interesting thing that you can start to see is that some materials start to get worse. So if you chose XPS that is expanded with a hydrofluorocarbon, you'll notice that at about R20, the curve inflects and starts to go back up, which means if you added more insulation beyond an R21 or so wall, you're actually the embodied carbon of that insulation is going to be worse than the energy that you would save. So this can start to help you shape how much insulation you might want if you're looking at global warming, total global warming potential. You'll notice the lines down here way at the bottom are going to be your cellulose, awesome insulation for inside a wall cavity, never outside. Your mineral wools are pretty benign down here because it's just melted stone. So there's some blast furnace energy, but not a whole lot else. But you can start to see that those just keep getting better. So the more insulation, the better. Obviously, there's a diminishing returns from a cost standpoint, but I just wanted to share that as a resource if you guys are working in studio and somebody happens to ask you about insulation, which I know always happens in studio every day, every project. They're like, how much insulation? Here's a really great resource that you can start to look at. Here's another one if we just want to look at embodied carbon. So this is not the energy side, not the efficiency of your building, but just looking at embodied carbon. But you can see XPS is just awful. It's a very high performance insulation, but it takes a lot of energy to make, and it's a fossil fuel based insulation. So they take oil and then they make it into foam, and then they expand foam, typically with a refrigerant. But even the XPSs that are CO2 expanded are not that great. But you can see sort of, you get down into your natural insulations. So cotton denim, recycled denim, wool. So cute sheep, shear them, make insulation. It's adorable. Dense packed cellulose is one of my favorites. Cork is great if you can afford it. And then you look at the supernatural, if you will, materials like hempcrete and straw bale. There's a really great resource if you're interested in straw bale construction right there in Berkeley at Arkin Tilt. David Arkin is a big proponent of straw bale construction. So if you're ever interested in that, I highly encourage you to go look at Arkin Tilt and their work. So that's the big picture. Materials matter. I'm going to walk you through a couple projects that I've worked on across my career focused on embodied carbon and the analysis that followed up, and then sort of decisions that were made throughout the process. So this is a project that I worked on a long time ago. Well, not that long, maybe 15 something years ago, while I was at Siegel and Strain Architects. This is the Portola Valley Town Center, so on the peninsula, not too far from Berkeley, but on the other side of the bay. And this is a new library, town center, city hall, and a small police substation. But very small building, kind of laid into the landscape, very simple. This is a story of rather than being able to reuse buildings, they had to be torn down. What you don't see in these graphs is on the left, which is was the existing buildings, that the fault line ran directly through 3 of the buildings. So these literally spanned a seismic fault. And during the last seismic event, I think the big Loma Prieta, one of the buildings actually shifted. So kind of broke in half a little bit. So not safe, couldn't use it. You can see the new plan on the right, built over an existing parking area, relocated, consolidated the buildings into actually less square footage. So that one ticket where I said earlier is size matters for embodied carbon. The original buildings, they had 25,000 square feet. In their new buildings, they actually got smaller. We were able to find efficiencies in the building. So that was that saved us quite a bit of carbon to begin with. And we obviously got them off of the seismic zone. Here's just some shots from inside. And I want to focus on a couple things that we did. So obviously there's a lot of natural materials used throughout the project. The one that I point to here, I don't know if you guys can see my pointer, but the window trim on all of the windows, rather than being field or sort of custom millwork, all of that was built from the shipping crates that the windows came in. So all the windows came to the site. We had actually one of the contractors break down all the shipping containers and then remill the shipping containers into building trim, so less waste on site. And you can start to see when we look at a breakdown of all the materials. So in this project, we actually took weights of every single piece of material in the building. So takeoffs from all the drawings, how much was going where. You see the biggest pie in the project is concrete. So there's a tremendous amount of energy, embodied energy that goes into concrete, specifically the cement mix. So cement, ingredient in concrete, has a huge embodied carbon associated with it. And so not only is it a very heavy material, it has a lot of embodied carbon and by far dwarfs anything else from a weight standpoint. on a small wood frame building. When we actually then shift that around, and now we did an embodied carbon takeoff. So each of those materials, even though concrete weighs the most, if we actually look at how much embodied carbon was in each material, you can start to see the breakdown. But concrete's still the biggest piece of the pie. So we definitely focused our attention on concrete. But you'll notice the building was going to be net zero energy, which 15 years ago was crazy. But the PVs actually have quite a bit of embodied carbon associated with them. Now that's offset by their energy production over time, and usually they pay for themselves back depending on the manufacturing processes in less than 7 years from an embodied carbon standpoint. But you can see all the materials sort of laid around, but you'll start to see a lot of embodied carbon associated with some of the other metal components. So cast iron piping, steel pipe, even though there's not a lot of it on a building that's wood framed, there's still quite a bit of carbon associated with them. So we went through a process on that project of actually trying to reduce the embodied carbon. We took a base case building and then said, well, what can we do? So on the far left here, you can see the big move within our concrete mix, going to a high fly ash concrete mix, nearly cut our carbon from concrete in half, which is a really big deal. There is the other one that I wanted to flag is over here on salvaged materials. So actually a lot of the beams on the existing buildings were salvaged out, remilled, regraded, and used in the new construction. And then all of the siding on that building was reclaimed from trees that were taken down on site for the construction process. So salvaged materials can actually make a really big difference. And if you, the AIA this week, I'll try to dig up a link and put it up on B-Course, but the AIA this week released a new design guide for building reuse and salvage. So if you're interested in designing buildings that can be salvaged at the end of their life, there's a new AIA guide to walk you through that process that I'd highly encourage you guys to read. It was written by some good friends of mine, super smart folks. So we often just talk about buildings, but remember when I talked about embodied carbon, the whole idea about embodied carbon is kind of looking outside your little dashed line. It was really important for us to understand actually how much the site work on the project used in carbon. So site concrete, asphalt paving, all the groundwork, et cetera. So all of the stuff that goes into site work, if you see, almost had as much carbon as sort of the rest of the big, heavy engineering pieces. So site work really matters too. Grading on site, those trucks that are used for grading are very low efficiency. They have zero emissions controls on them at all. And so they actually have a big carbon footprint as well. So areas that we were able to actually save a lot is, you'll notice that the little chunks of carbon right here for base rock and CMU off-haul were really low. So on this project, for the existing buildings that we had to tear down, we actually brought in the machines that break up concrete and broke up all the existing foundations into base rock, into gravel, and used that as the gravel for the new buildings. And so we could avoid bringing in rock that had to be mined somewhere, and we also saved all that waste concrete from being shipped out somewhere. So just think about the entire sort of process of your building. What on an existing site could you reuse for new construction? So all in all, those strategies reduced the carbon footprint of the project by about 15%, 14%, which in our heads is like, oh, well, it's not that great. But remember that that 14% is on day one. It's like right there. It's not over the life of the building. It's like immediately the day the building opens, our embodied carbon was significantly less than a brand new constructed building. And they got brand new constructed buildings. So it's really important to walk through that. So the lessons that we learned from that project, and these are ones that you guys can sort of take forward, even if you don't have time or capacity to do a full life cycle carbon assessment from your building. is step one, tackle the materials that you have the most of on your site. If you're building a steel building, focus on the steel. How can you economize the steel? Can you get recycled steel instead of virgin steel? Are there structural systems that you could do in lieu of steel? That's a big one. I'll talk about that in a little bit. You want to try to limit your high carbon materials. So these are concrete, steel, and aluminum. Aluminum is really bad. I'll talk about that in a little bit. And where you can, salvage and use recycled materials, because it actually really does make a difference. And I know it sounds super cliche, buy local, farm to table. Local makes a really big difference for embodied carbon. If you think about those heavy materials that you have for a project, having them come from across the country uses a ton of energy and emissions associated with that to get something here. So that fancy Italian marble that a client really wants on their bathroom lavatory, oh, come on. Like, you're shipping something all the way across the country, and not only that, or all across the world, but it's also exceptionally heavy material. And so you're kind of getting dinged twice for that. So that's makes us all sad inside, and our little carbon hearts cry.
Stet,
yeah.
Stet, can you go back a slide for
Sure.
a moment? Nope, the lessons learned.
Yes.
So there was a question on chat that I'll read for you. A question from Peter: what's the approximate increase in cost of using lots of fly ash in a project this size? And does it impact other choices such as structural?
Yeah, so there's a limit on how much fly ash you can add to a concrete mix and still hit the compressive strength, the PSI of the concrete. And so 35% is pretty high. That's kind of the max that I've seen out in the marketplace of going to a 35% offset. So you're offsetting 35% of your cement with fly ash. Currently, we don't see a price premium for fly ash. 15 years ago, we certainly did. But right now, if you source anywhere in the Bay Area, like Central Concrete does most of the concrete in the Bay Area, or a good portion of it, they have a non-premium on their high fly ash concrete. The one caveat that I would add whenever you're doing with non-traditional concrete mixes is that if you're doing concrete staining, so there are integrated stains that you can put into concrete to get different colors, like the super white concrete is, it's actually what concrete looks like, but you can stain it to be like darker gray or tones of red. I mean, there's all sorts of things. Those stains interact with fly ash very differently than they do with traditional cement. And so some weird things can happen. So I definitely recommend doing test pours before a big pour if you're looking for a polished concrete floor.
That's great. And just a note to the students, these kinds of generalized lessons learned, this was a great case study, Stet, great generalized lessons learned. This slide is the kind of thing that could show up on an exam. Wink, wink.
Wink, wink.
All right, back to you, Stet.
Yeah. Sure. So we have these two things that seem to be fighting in the industry. We're like efficiency, 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 operations carbon, and then embodied carbon. And we keep thinking about this like over 100 years. Like, oh, well, you know, we should only care about operational energy because in 100 years, look how much it dwarfs embodied carbon. Like if you look at 100 years, embodied carbon of those materials is only 8% of the total pie. Well, we don't have 100 years. One, we'll all probably not be here. But the world does not have 100 years. When we look back at the climate projections, if we don't actually address carbon today, we might not be building in 100 years because your site might be flooded. So climate change has taken what we normally thought of as a 100-year lifespan for a building and really truncated it. So we really need to focus much smaller. So even if we do a really efficient building, that 100 years doesn't look that much better for embodied carbon. Now it's 13% of operating. But like I said, the real issue is that first little window, 20 years. We need to cut carbon emissions today. And if I focus on a 20-year lifespan, so the next 20 years where things are going to get real, then all of a sudden the embodied carbon of a project is almost half that of operating carbon. And so you actually start to see the real importance of focusing on embodied carbon now because all of those emissions happen the day the building opens. So if a building is starting construction today, or starting design today, it's probably going to be built in 5 years. That carbon, all of it is released within that window. And then after that, you have your operations. So we shouldn't think about these two things as fighting each other. We should think about them cumulatively over the next 20 years. The embodied carbon is kind of the base that it just starts with on day one, and then the operating carbon builds on top of that. So for a code-compliant building, it's really awful. We want to do a low energy building and low carbon building so we can shrink that, if not make it negative. And I'll talk about some strategies for doing that. Okay, so here's the big break. Well, it's kind of a break. Please don't walk around and go have tea. But we'll give you guys a chance to get ready for the quiz. So we're going to start the quiz right now. And for everybody who is watching a movie on the side, kindly pause it. And
wait. Don't say start right now.
Sarah, no, yeah.
Terry, that didn't mean start the timing yet.
Right.
So when you said the word start, that wasn't the real start.
The fake start. I want to give everybody time to make sure that they have another tab open and go into B course. And you guys can see the link to where the quiz is going to be. So it's under B course, it's under syllabus, week 10. Today, April Fools. So, haha, quiz. And then you'll be looking for quiz number 4. So I want to give everyone some time to find that. Again, we're not trying to cause stress.
Mary just made a comment. Yeah. We're going to tell you when the timer starts, so we don't want anybody to panic. All right. Caitlin just said, is the quiz locked? So yes, it's locked for the moment. We just want to give everybody a chance. Somebody asked if you can repeat where it is. Just look at the slide right now. If you go to the syllabus, week 10, April 1, quiz 4, there should be a link. And Carrie just added a comment. So you can get to the quiz and you can see the front page. So you know that you're there, but she's going to wait to open it so that we give everybody plenty of time.
We just open it in B courses?
Yeah, you should be in the B courses tab. So you can go to the syllabus and there's a direct link. You can also on the left side go to quizzes and scroll down to where it says quiz 4. That's another way to take you to the same place. So when you get there, you'll see the front page. You'll see the same instructions that I sent you in an announcement, and what you see here on the screen. Just to know that you have a total amount of time. Unlike when we were in class, when we time per question, this is a total amount of time. So it's a little bit more relaxed. It's a lot more time than we give you per question when we're in class. Very important though is this last bullet that you're seeing on the screen, that you must answer each question before moving on. But once you move on, you can't go backwards. So we don't want you to think that you can go back and change your answer. So I want you to be reflective on each one.
But we will have more time per question than we normally do. So.
And when the whole quiz is done, just as we do in class, we'll go back and we'll give you the answers to each one. All right, so I think we should be ready. I don't hear any more questions. I don't see any more questions in chat. So Carrie, take it away.
All right, the quiz is now unlocked.
So this is the official start.
Yes.
Okay.
12 minutes.
Okay, we'll see you guys in 12 minutes.
Hey everyone, I just wanted to let you know that we're 6 minutes in and you still have 6 minutes left. So everyone, we have 1 minute left. if you feel like you need more time, if you could go ahead and use the chat function and let us know. But right now, we've got 1 minute left. But please write in the chat window if you need a few more seconds.
Okay, I think just one more minute. All right, I'm going to go ahead and stop the share of my screen. And we're going to go ahead and stop the quiz now.
And Gail, are you going to go through answers because I don't have them locally?
I also just realized that I need to probably open up an old, well, hold on. I have to open up the questions because I don't want to go through them on B courses. So let me see if I can find them on a PowerPoint. Oh, I'm probably still muted. No, I'm not.
Nope,
muted.
you're on.
Okay. So let's go through the questions, and they're not necessarily in the order you got. So the shading mask question, the correct answer was, this was the egg crate. And you can tell that because it had both the overhang represented by a profile angle and the fins represented by azimuth angles. Next question, which of the following is true of vertical shading devices? The answer was both B and C, which was in a south orientation. They're good for blocking early morning and late afternoon sun. Plus, if the fins are infinitely long, they're represented on a shading mask using azimuth angles. Next question about the solar heat gain coefficient. The question was, the lower the SHGC, the less solar heat is emitted, true or false? The question is false. Wait, no, sorry, I just, the answer was true. The lower the number, the less solar heat is emitted. And I was confusing that with this next one, which was the limitations of the Energy Star program is that its recommendations for U factors don't account for the different climate zones, and that is false. They absolutely do account for different climate zones. Fifth question, NFRC is an acronym for National Fenestration Rating Council. And the final one, which of the following are possible objectives of a thermal simulation program? The answer was all of the above. And now back to you, Stet.
Thank you. Let me see if I can make the magic happen again. Let me know, can everyone see my screen again? I'll try to get my chat up. Perfect, thank you. Okay, so for the last 20 minutes, I'm gonna go through a couple more case studies and just talk about some strategies for projects. So, you know, I talked about building reuse as a really great strategy, but another, to sort of take that to the next level, oh wait, sorry, I'll share my video again because I'm sure that's gonna keep everyone up at night if I don't. One of the best strategies we could think about is building reuse, doing deep efficiency measures on those buildings, and then taking those buildings beyond net zero to be able to go to net positive energy. So we're going to talk about an example of a project where we did just that. So this is local, super close. It's in San Francisco. It's actually just a few blocks from my office. This is the DPR construction headquarters for San Francisco. And it is on Front Street. So actually in the background here in the image, you can see the Exploratorium, another project that I worked on. But yeah, the DPR office is just off the wharf on Front Street. But it's a net positive retrofit. So I'll talk a little bit about that. Here are some photos of inside. So when DPR found this building, it had no skylights. It was this dark building sort of chopped up into like 100 offices, little offices with no windows, no natural light, nothing. And so the interior, a lot of the interior partitions were stripped out to open up. This is the lobby when you walk in. You'll notice just some cues of biophilia, an actual court, interior planted courtyard, as well as the living wall. A big focus on the material or on the project was salvage materials. So anything that we could salvage from construction, we did. So a lot of the furniture is from either this construction site salvaged or other DPR construction sites where they had materials that were able to be salvaged. So this is a second green wall you can see sort of on your right, and then a large skylight that was there but boarded over on the existing building. We reopened it and added dynamic glazing. Some other reuse stories on this project: the tables in the dining area are actually reclaimed bowling lanes. So if you see these little markings, I don't know if I can, let's see if I can do something fancy, or for me fancy. Forget it. But these tables are reclaimed bowling alleys. You can actually start to see the little markings for alignment. And all the wood above the eating area ceiling, the wood slat ceiling, was all reclaimed. Otherwise, the structure was kept intact as much as possible. There were some seismic upgrades. You can actually see just to the left, a new seismic brace here. Cross brace was added because the building wasn't formerly seismically safe. But a real emphasis on opening up the building, getting natural light into all the spaces, even the conference rooms that are sort of inboard. And a special note, like the concrete slab on grade was kept because remember back to our story earlier about concrete being this huge embodied carbon. Wherever possible, the slab was kept intact, and we actually just ground it down a little bit and polished it. And so a real focus on trying to keep the durable materials durable and try to not replace them wherever possible. There was some structural work that was required. So image on the left here, you can see the steel here, these steel girts as part of the truss were added because the original truss, barrel vault truss, was actually wood, but was way undersized for current California seismic code. So there was some new steel added. Also, we needed to be able to support the weight of the PVs on the roof. So a little bit of new structure is added. Like I mentioned, the image on the right, there was a skylight that was there, but it was completely covered, so you couldn't see it from the inside. So you had all the worst things about a skylight: heat loss, heat gain, but you didn't get any of the good things of the daylight. So that was opened up, and the glass was replaced with dynamic glass that can shade itself or tune down to really low solar heat gain coefficient to provide daylight, but also mitigate heat gain. People love it. When you guys get out into the field, I highly encourage you working with DPR. They're a really fun contractor. They throw great parties. Side note. The reason I want to bring up this project is because after we were done with the engineering, once they moved in, we actually did a full life cycle carbon assessment. And so I want to talk to you about some of the results that came into those. So the two scopes, really we looked at full scope emissions. So scope 1, the building emissions, scope 3, all that embodied carbon, and scope 2 I didn't talk about earlier, but that's the energy that you procure somewhere else. Our project doesn't really have scope 2 emissions because it's a net positive energy building, but other projects that might use grid power would have scope 2. So what we did for the comparison is we actually, in Revit, we built a brand new building that was the same square footage, same footprint, using today's construction standards, like typical buildings. And so we built one of those and did a baseline energy model. So it has an EUI of 60. And then we compared it to DPR's office for scope 1, 2, and 3 emissions and total carbon. You'll notice that the energy use intensity, the EUI, was a third of what a typical building was. We got it down all the way to an EUI of 20, which is really good for a 2-story office building. And then, but the big story is the difference in the scope 3 emissions. So a big drop in that embodied carbon piece, so not just operationally, but a big drop in the carbon emissions by reusing the building. You'll notice no scope 1 emissions because we have no energy burned on site. Scope 2 is the power that we needed to buy from the utility. Well, we didn't have any because we're a net positive energy, at least if we look at a full year or a 50-year life. So actually this building over a 50-year life sequesters carbon because it's offsetting other people's energy use because we're a net positive building. And the big goal for us was trying to find a building offset where over a certain lifespan, our carbon offset or our overproduction of energy would offset our own embodied carbon. And so you can see that within a 50-year lifespan, we definitely do that. But I mentioned that 20 years is the time to act. And so we did the same model, but then we compared it to a 20-year lifespan. And you can see that the embodied carbon, or the positive energy that we produce, doesn't quite offset the embodied carbon for the project within the 20-year lifespan. But it's way better than sort of any other project that I've seen out there. But this is an area that we're focusing on now, is trying to say, well, can we do a retrofit where the carbon savings on the net positive side of energy, can we design in such a way that our embodied carbon is so low that we actually offset or even more than offset and make the building itself a carbon sequesterer. So that's sort of the goal from a design strategy. And we think we're on the path. So quick poll. So we're going to have Gail pull up the poll everywhere again and give you a second. Again, this is not a graded thing, so no stress if you can't get to your phone or to the online log. But when we did this retrofit, what do you think? What do you think we saved the most carbon by reusing in the building? Is it going to be in the carpet systems, because there was some carpet reused? Is it in the structure? Is it curtain wall mullions, roofing? Where do you think the big carbon savings was? I would say pretty loud response in the structure category, possibly the roofing, not so much in the carpet. Okay. Interesting. There's a few votes in the curtain wall mullions. Again, the aluminum curtain wall. See how it shakes out. Okay, well, I'm gonna share. Is it okay, Gail, if I hop back?
Yeah, go ahead.
Perfect.
I just done.
Oh. So this is a look at that embodied carbon. The dark colors is where we landed. So the fully filled in colors in the at the sort of bottom of the graph are where our building landed, and the hashed sections above are the savings. So what we didn't have to do by not building a new building. And so you can see huge impact of reusing the floor. So a lot of carbon in that concrete, and by so that to a certain extent, the flooring, if you will, actually saved quite a bit of carbon. It wasn't the carpet, so we didn't reuse any of the carpet because it was pretty gross. There was a lot of savings in the walls, only because this building happened to have on the sides these like 16-inch thick concrete walls that we didn't touch. But we wouldn't have to do that in a new building, so that bar is a little questionable. But I want to point out two areas. The curtain wall aluminum actually had a tremendous amount of carbon in it, and so we worked really hard to maintain that where we could, and only have to replace certain amounts. But you guys are, most of you are right, the big savings is in the structural system. So the concrete structural system and the existing deck, trying to keep that, you will see that we had to add a little bit extra structure for the seismic, but huge carbon savings in the structure by reusing the building. So very exciting for us. But again, it goes back to those lessons learned, even back to Portola Valley, of focus on the materials that there are a lot of. So there's a lot of structure in a building, and focus on those materials that have the high embodied carbon, rather than, we're not going to spend a lot of time focused on ceiling tiles or stairs and railings, because those are not huge ticket items. We're not going to move the bar tens of percentages with those. I'm going to go through this really quick because I also want to show another project, but this is looking at those, again, scope 3 embodied carbon emissions, but a big piece of that is in the new PV system that went up on the roof, which is really important. Just to give you an idea, you can dive even deeper within scope 3 emissions and understand the impact of manufacturing, as well as sort of ongoing maintenance and replacement over life and end of life for each material. The big stuff is on the manufacturing side, so that's where we wanted to focus. But you can do a lot at the end of the life of the building. Again, if you design your building for reuse, if you design your building for salvaging at the end of life. So how do you bring materials together so they can be taken apart without a heavy demolition crew? Those are really important things for end of life embodied carbon. At the end of the day, though, for us, for this project, we were able to reduce embodied carbon by 70% compared to a new construction building by reusing an existing building. And that's a huge deal, especially in that current time frame, that short duration. So here's our sort of hypothesized standard building. We want to focus on low embodied carbon up front and going net positive. The idea is that within 20 years, we want the area above the curve of net positive to equal or be better than the area under the curve of our embodied carbon. We want to start looking at true carbon neutral buildings that offset not just our energy use, but other people's energy use, so that we can truly offset our own embodied carbon. So after Portola Valley and after DPR's office, when I was still at Integral Engineers, we actually went on and did this in 6 more buildings in the South Bay with Sharp Development. So we did a bunch of net zero and net positive energy retrofits of existing buildings. And we were doing them at developer cost. So these did not cost any more than a normal developer-led project. So really fun stuff. But if you guys have an interest in going into the development side of the world, I highly encourage you to look at Sharp Development down in San Jose. Great group of folks there. So there's some tools that we used in this, and one of them was obviously Revit for the building side, but going into a program called Tally that was developed by Karen Timberlake, and then EC3 that has been developed up in the state of Washington, at University of Washington, with the Carbon Leadership Forum, which is a phenomenal resource for embodied carbon. You can dig into this. I don't want to go into this too much because I want to talk about another project really quick before the end of class. We still have about 5 more minutes. But when we talk about embodied carbon, and we talked just a few minutes ago about structure, there's a huge difference between the different types of structures that you can use and the embodied carbon associated with them. And so a lot of you are probably aware that there's a big push right now in heavy timber construction, cross-laminated timber construction, or the broader category that we call engineered wood. And it's kind of been driven by the Pacific Northwest, where there's a lot of wood available. But there's been quite a bit of carbon assessment of looking at different structural systems. And for most regions on the West Coast, engineered wood, cross-laminated timber, heavy timber is a clear winner from an embodied carbon standpoint over traditional concrete or steel buildings. Now, they don't have the same thermal mass, and so I would, I don't want to say carte blanche that every project should be heavy timber, because there's still a lot of really exciting things you can do with concrete, with load shifting and radiant. But engineered wood buildings from a carbon, embodied carbon standpoint, in most cases along the West Coast, are significant embodied carbon savings, and can be really fun. So with the last couple of minutes, I want to talk about the last office we have, the project out of my office that we just finished, and it just opened a couple months ago. So this is the new DPR office, again, one of our favorite clients, the DPR office in Sacramento. And this is an adaptive reuse of an existing building to turn it into a construction office. It's going to be hopefully net positive energy, but right now it's trending at net zero. We'll see after the first year of occupancy if we can get it up to net positive. And in this case, we wanted to do all the retrofit structural work with CLT, cross-laminated timber, sort of heavy timber construction. So you can just sort of, anything that is wood, you can see as new. And it's sort of a nice diagram of concrete was the existing structure, everything wood represents new. So you can even see in this image where the waffle slab of the existing building was cut, so that we could add a new communicating stair between the 2 levels. Here's a shot from just a little bit far over, but you can see the project, a lot of solar tubes added for daylighting, so the space is 100% daylit during daytime hours, so our daylighting factor is 100% within working time, within daylight hours. But really nice use of CLT sitting on top of an existing structure and penetrating down where it needed to. On this side of the building, this is the existing side of the building, but completely renovated. Again, a lot of natural daylight from solar tubes, as well as you can see the existing steel structure and decking above, so that was all kept in place. New high efficiency ventilation, DOAS, and VRF, and we'll talk about that next week when we start to talk about HVAC systems. But some really low energy HVAC systems, flexible workspace, ceiling fans, which go back to Gail's discussion of passive cooling strategies. In this case, part of the roof was actually cut back from the building to actually do, so this is part of the existing building. We cut the building back to allow an outdoor patio space on the 2nd floor. And you can see part of the PV system extending over that to provide south shading of the sort of opening wall. So with that, the big, there's a question before I drop off. How exactly do solar tubes work? I'll try to dig up some images to share with you. But effectively, these are highly reflective tubes that go up, and they have a lens on the top that is engineered to take light from a lot of directions and scatter it inside and sort of focus it down. And then at the bottom, you have a diffusing lens. Typically, these are only going a few feet. We don't often see them going down much more than that because you start to lose efficiency within the solar tube when it comes out. regarding CLTs and recyclability, yes. So if you design these beams these all had blind steel connections inside, but they are dismantleable. But glue lamps themselves can be reused, but they're not great at being like recycled, if that makes sense, because the glue lamps have glue in between each layer of the wood. So as long as the structure, the whole piece is there, they can easily be reused for other structural applications, but they're not easily taken apart and reconfigured. So if you needed a beam that size, awesome. The nice thing is the manufacturing supply stream for glue lam for heavy timber is very clean, especially if you're sourcing from Washington forests. So most of them are manufactured in Washington, Oregon. Right now, there's, I think, one manufacturer in Northern California, but sourced not too far away. And the nice thing is when they're down in their components, they're actually quite easy to ship because all the pieces can stack, and you can get one truckload that has a lot of the panels, which provide the floor, and the beams as part of the system. So all in all, we're super excited about movement within embodied carbon. And with that, I think we're at the end of time.
Wow. And I am going to unmute everybody so we can give everybody that a round of applause.
Thank you. Thank you, everybody.
Thank you.
Thank you so much.
Stay safe. Don't touch anybody.
Nicer close.
Thank you. Hey, guys.